Coming here to listen to my talk. The title of this talk is that all planar graphs other than C5 are for dynamically colorable. This is joint work with Sangjune Kim and at Konkuk University and Wonjin Park at Seoul National University. Okay, so if you read the title, you will be familiar with almost every word except for dynamically. So as you see this title is related to the four-color theorem. So all planar graphs are four-colorable. But in here, we will think dynamic coloring with extra condition from the proper coloring. And when we consider dynamic coloring, and we will show that all planar graphs other than only C5 are for dynamic colorable. Right. So let's start with the definition of dynamic coloring. A dynamic coloring of a graph G is a proper coloring of the vertex set Vg such that each vertex of degree L is 2 has two neighbors having distinct colors. So if there is a vertex of degree L is 2, these two neighbors should have distinct colors. So first, you want to know that why we want to study this kind of new definition. So we can find the reason from the relationship between the vertex coloring and a partition of vertex set. As you know, a proper coloring corresponds to a vertex set partition such that each part is independent, right? So like that, a dynamic coloring corresponds to a partition of vertex set such that the following holds. First, every part is independent, which is from the proper coloring condition. And second condition is like this. So every vertex of degree L is 2 has two neighbors in distinct parts. This green condition is from this green condition, right? So what is good thing to study this coloring? So if we have a dynamic coloring, that means that we have a vertex set partition such that whenever we have a vertex of degree L is 2, there are two neighbors which are in distinct part, right? So which means that if all neighbors are here, so if the degree of this vertex is 2 or more than that, this kind of thing, such that all neighbors are in a same part, is impossible, right? So why this is good? So maybe we can apply this thing for some assignment problem. So let's assume there is a company, and they may want to. The company have several departments, and the company want to assign each person to each department, right? So if we use this way, then each person will have very close friends in at least 2 departments, right? So this person maybe co-work with at least 2 department people, right? So that maybe increase the efficiency of the company, right? On the other hand, we can use this for other reason. So if this edge is about some enemy, then the chairman of the company maybe think about this kind of partition. Then each person can be controlled by at least 2 enemies from 2 different departments. So that might be useful, right? When somebody wants to control one person, right? Okay. So with this definition of dynamic coloring, we can define dynamic chromatic number. So our dynamic K coloring of a graph is a dynamic coloring with k colors, and the dynamic chromatic number chi d of g with extra d is the smallest integer k, such that g has a dynamic k coloring. Okay, so let's just start with a simple example. So we will consider C5, and we want to know what is the chromatic number of C5 and dynamic chromatic number of C5. So first, about chromatic number, as you know, we can give color 1, 2, 1, 2, and for the last one, we should introduce new color 3. So 3 colors are enough for a proper coloring, right? But let's think about dynamic coloring of C5. Okay, so for the first vertex, we can give color 1. And for the second one, to satisfy the proper coloring, this color should be different from this. So this should be 2. And what about the color of the third vertex? First, we want to give 1 for this color, but which is not good, because if we give 1 for this vertex, then this vertex will have 2 neighbors which has same color, right? So which is not good in view of dynamic coloring. So this should not be 1. Also, this should not be 2 for a proper coloring. So this should be new color 3. And what about the color of this? First, we want to try color 1, but which is not good, because if we give color 1 for this vertex, then in view of this vertex, 2 neighbors will have same color, 1, right? So which is not good. So 1 is not good. And with the same reason, we can't give 2 because of this number 2. So and also for a proper coloring, we can't give 3 for this. So the color of this should be new 1, 4. And with the same reason, this color should be new 1, 5. So for C5, dynamic chromatic number is 5. So as you see, even though C5 is a very simple graph, the chromatic number and the dynamic chromatic number may be different, totally different, right? Okay, so what will be problems? So basic problem will be as follows. What is the dynamic chromatic number of a given graph or a family of graphs, right? But with the relationship of four-color theorem, one of the most interesting problem about dynamic chromatic numbers is to find the upper bound of dynamic chromatic number for planar graphs, right? So let me start with the previous results. Chen, Fan, Lai, Song, and Soon in 2012 showed that if G is a planar graph, then the dynamic chromatic number is n-5, which is 1 bigger than the upper bound of chromatic number for planar graphs, right? So, and actually this is best possible because the dynamic chromatic number of C5 was 5, as we did, right? So this number 5 is best possible we can get, right? And after that, Kim and Park in 2011 showed that if G is a planar graph with girth at least 7, then the dynamic chromatic number is n-4, right? So this upper bound 4 is like upper bound for four-color theorem, right? But we have some extra condition about girth, right? And next, actually, among the people who studied the dynamic chromatic number, the conjecture was the following. If G is a planar graph other than C5, then the dynamic chromatic number is n-4, which means that this is only exception, and except for C5, the upper bound of dynamic chromatic number is 4.
So you mean the connected flat?
So in case of disconnected, then then we can give color separately, right?
Right. So then one of the component might be C5.
Right. There might be an embedding of C5 somewhere.
Uh-huh. Yes, that's right. So, right, that's right. So if we have some C5 in a component, as a component, then this will be bigger than 5. So, right. So, yes, I need to add connected here, right. Okay, so Kim and Park and I showed that this conjecture is true, right? And also, we can consider least coloring version for dynamic coloring. So let me first define least coloring and choice number. Maybe some of you already know the definition. For every vertex V, let LV denote a list of colors available at V. And on L coloring is a proper coloring such that the color of each vertex V is chosen from LV. And a graph G is called K-choosable if it has an L coloring whenever all lists LV of L have size L list K. And the choice number, CHG, is the least integer K such that G is K-choosable. And we can define dynamic choice number. So in a similar way, so a dynamic L coloring is a dynamic coloring of G, which is an L coloring of G. And a graph G is called dynamic K-choosable if it has a dynamic L coloring whenever all lists LV have size L list K. And the dynamic choice number is the least integer K such that G is dynamic K-choosable. So simply you can understand that dynamic choice number is the choice number with a dynamic coloring. Right.
So how would you define LV?
So for dynamic choice number, so enemy can give LV, any list.
Pick any list.
Right. Enemy can give any list with this number of this size. Then we can color the vertices, right? Okay, so previous results about this direction is the following. So first about the choice number, Thomason in 1994 shows that G is a planar graph, then the choice number is at most 5, which is one bigger than the chromatic number in the four-color theorem, right? And about dynamic choice number, Kim and Park in 2011 showed that G is a planar graph, then the dynamic choice number is at most 6, right? So this is one bigger than the upper bound of choice number, right? And Chen, Fan, Lai, Song, and Soon in 2012 showed that if G is a planar graph with a maximum degree at most 4, then the dynamic choice number is at most 5. So this number is tight with the upper bound of choice number, but we have some extra condition here about maximum degree. Okay, so also the conjecture was the following in this direction. If G is a planar graph, then the dynamic choice number is at most 5, which is tight with the upper bound of choice number, right? And now there is no other condition, right? And our argument can be applied in this direction, so we can show the claim, right? Okay. So let me mention about the method. So for these two results, we use elementary argument such that minimality and induction. This is a very interesting thing because usually for a new result for vertex coloring nowadays people use this intercharging argument or probabilistic method, but yeah, interesting. So but we used elementary argument to get this kind of nice result. Okay. Of course, we need to add some ideas. So that idea is about edge-addable graphs and edge-added graphs. So let me define what is that. Okay, so for edge-addable graph and edge-added graph, you can think this figure later. So let me first define that with a statement. A planar graph G is called edge-addable if there exists a supergraph H with the same vertex set satisfying the following. H is also a planar graph, and every vertex v of degree at least 2 in G has two neighbors in G which are adjacent in H. So let's see this example. I have that. So let's see this example. So there is a graph. So I will say this graph is edge-addable because after adding some edges, some red edges, right, we have a supergraph like this. And this supergraph satisfies two properties. First property is this is still planar. And secondly, for every vertex in G of degree at least 2, two neighbors are adjacent with some red extra edge, right? So does it make sense? Right? So we want to add some extra edges to G to satisfy that every vertex here, for every vertex here of degree at least 2, two neighbors are adjacent with some extra edge, right? And we say that this is edge-addable graph, and we say this is edge-added graph of G, right?
So do you allow edges to be in G as well? When you pick a vertex and look at two neighbors, if they are already adjacent in G,
right,
is it okay?
So I think, yeah, so if you see this figure, actually we don't need to draw this new edge, right? Because for this vertex, two neighbors are already adjacent. So actually, we don't need to consider about this red edge, right? So like this could be edge-added graph of G because for this vertex, two neighbors are already adjacent in G. And also one more thing is, we don't need to have the multiple edge, right? So one edge is enough to, so two edges do not, doesn't mean anything, right? But formally, let's try to draw red edges for every vertex to satisfy the condition. So just formally.
So when you say neighbors, is it a neighbor in G or H?
In G.
In G.
Right. So for example, for this vertex, there are two neighbors over. For this vertex, this and this are neighbors. So we connect this red edge. We draw this edge. And for this vertex, two neighbors are this and that. So we draw this red edge. And for this vertex, two neighbors are this and that. So we draw this edge, and so on, right? Actually, yeah, so we don't need to draw this red edge, but let's formally draw red edges for all vertices of degree at least 2. Right.
So the top right vertex, two neighbors. No.
This one?
Yes.
Yes.
There's two neighbors which are not connected by a red edge.
So for this vertex, there are 3 neighbors.
Yes.
But our condition is about the following. So there exist 2 neighbors which are adjacent.
There exists.
Right.
Not for any.
Right. Not for any. Right. That will be stronger condition. Right. Right. Okay. Right. So maybe you need to keep this in mind for this talk. So I draw this figure. So this is edge-addable graph, and this is edge-added graph of G. Okay, so why we think this kind of new definition? That is from the following claim. So we want to connect proper coloring to dynamic coloring. So this claim gives us that. Let H be an edge-added graph of G, then a proper coloring of H is a dynamic coloring of G, right? Let's assume that we have a proper coloring of H, right? Then since two neighbors of a given vertex are adjacent, right? So two neighbors should have different colors, right? So if we use that proper coloring, then over here, that satisfies the dynamic coloring condition for the original graph G, right? That's why we think this kind of supergraph, right? Okay, so and we can think the following observation. If a planar graph G is edge-addable, then the dynamic chromatic number is at most 4 and the dynamic choice number is at most 5. Let's prove that. Since G is an edge-addable graph, then there exists a graph, supergraph H, which is an edge-added graph of G, right? And since H is planar, we know that the chromatic number of H is at most 4, and the choice number of H is at most 5. And by the previous claim, a proper coloring of H is a dynamic coloring of G, so which gives us the dynamic chromatic number of G is at most 4, and the dynamic choice number of G is at most 5, right? So we can translate the chromatic number and dynamic choice number to dynamic chromatic number and dynamic choice number of G, right? Okay. So with this observation, we will show the following key lemma. Every planar graph other than odd cycles is edge-addable. So we need to show this key lemma. Then by this observation, we can show the following corollary. If G is a planar graph other than odd cycles, then the dynamic chromatic number is at most 4, and the dynamic choice number is at most 5, right? Okay. Then this is our main theorem to show. So our main theorem is about almost every planar graph, right? But currently we have some condition about other. We just exclude odd cycles. But actually, for odd cycles, the dynamic chromatic number and the dynamic choice number is known. So they are bounded by 5 if the odd cycle is C5, and they are bounded by 4 if the odd cycle is C7, C9, etc. So if we combine this corollary and this result for odd cycles, then we can get our main theorem, right? So every planar graph other than only C5 satisfies the dynamic chromatic number is at most 4, and every planar graph satisfies the dynamic choice number is at most 5. Right? So just we can combine two results, right? Okay. Right? So we need to show the key lemma, right? So stating that every planar graph other than odd cycles is edge-addable. But first we will consider two connected planar graphs. So we will first show the weak key lemma, which is only for two connected planar graphs, right? So first we will show this weak key lemma, and then we will show key lemma from this weak key lemma, right? So why we should think about two connected planar graphs first, right? That's because two connected planar graphs have nice properties. Two nice properties. That is about the following. So first property is the following. So if G is a two connected plane graph, then the boundary of each face in G is a cycle. Okay, so I draw two examples. So first example is about a planar graph, which is not two connected, and second graph is a plane graph, which is two connected. So if you see the first graph, then let's think about the statement, the condition, the boundary of each face in G is a cycle. That is not true, because when we consider outer face, the boundary is like this, right? So which uses this edge twice, right? So the boundary of the outer face is not a cycle, right? But if you see this example, then you can check that the boundary of each face are cycle, is cycle, right? So actually we can show this is true, right? And the second property is the following. If G is two connected plane graph, then each vertex of degree D in G is incident with D faces. So if we see the first graph, this is not true, because let's think about this vertex. The degree of this vertex is 3, but the number of faces which are adjacent with this vertex is 2. This face and outer face, right? But in case of two connected graph, we can show this is true, right? So these two properties will be used to show our wiki lemma. So so that's why we first need to think about two connected graphs, plane graphs. Okay, so let's show the wiki lemma. So outline is the following. Fix a planar embedding of G, and for simplicity denote the embedding by G. And let f of G be the family of drawings H on the plane obtained from the planar embedding G by the following procedure. For each vertex V of G, add one red edge between two neighbors which share a face, right? So let's think about this is G, then so for each vertex of V of degree at least, so for each vertex, so we will connect two neighbors which share a face like this, right? So we will have a bunch of this kind of drawings, which is a supergraph of G, right? Actually, among those members, if there is a planar one, then that means that this original graph is edge-addable, right? Because that planar one will be the edge-added graph of the original graph, right? But there is no planar one, then this original graph is not edge-addable, right? Because if we add edge, there should be some edge crossing, right? So that's why we think this family. So we want to show the following. F of G contains a member which is a planar embedding, right? Then this is equivalent with the condition that G is edge-addable, right? Okay. So for this, we define the following. Let CRH be the number of edge crossings in H, and let H mean be a member of f of G such that the crossing number of H mean is the minimum of the crossing number of H, where H is in f of G. Then we claim that H mean is a planning embedding, right? Okay, so if we show this for every graph G, every two connected planar graph G, there is a member H mean which is planar in f of G. So the graph will be edge-added graph of G, so G is edge-addable, right? Okay. So we want to show this is true. So we will use contradictory proof, right? So suppose that H mean is not a planar embedding, that is, the crossing number of H mean is positive equivalently there is some edge crossing in H mean, right? Then we will show that there is a member H prime such that the crossing number of H prime is smaller than crossing number of H mean, right? Then it contradicts to the minimality of crossing number of H mean. So therefore, this assumption is wrong. So H mean should be a planar embedding, right? So we need to show this, right? We need to find some member H prime such that the crossing number of H prime is smaller than the crossing number of H mean, right? So we will find H prime from H mean. So let's start with setup. So under the assumption the crossing number of H mean is positive, there are two red edges in H mean cross each other, right? So there is an edge crossing. And let H be the family of G where the edge crossing occurs, right? And let VF be the set of all vertices in the boundary of face F in G. So for example, if I draw a figure, this is H mean, right? And by the assumption, there is some edge crossing between two red edges, right? So let's take the face as F, the face in G as F, right? So this face as F, right? And the vertex on the boundary of F is called VF. Okay, then we will do the following. Step 1, we delete all red edges of vertices in VF from H mean. And let H0 be the resulting graph, right? So this is H mean, but since there is edge crossing here, we want to remove that. So first we remove the red edges of these vertices. Then we will have this kind of graph, H0, right? So we remove the one edge crossing, right? And then step 2, we add the new red edges of vertices in VF without edge crossings. Let H prime be the resulting graph. So from H0, somehow we will add the red edges of the vertices on the boundary of F without edge crossing, right? So in this figure, we can add this kind of purple edges, right, without edge crossing, right? Then we will infer the following. So the crossing number, and this H prime will be a member of FG because now every vertex of degree at least 2 has its red edges, right? Okay, because we added the red edges of these vertices, right? So this is a member of FG, right? And let's compare the crossing numbers. The crossing number in H prime will be same as the crossing number of H0 because when we add some red edges, there was no edge crossing, right? So the two crossing numbers will be same. But what about this? So we remove the one edge crossing here, right? So the crossing number of this graph will be smaller than the crossing number of this graph, H mean, right? So this H prime, the crossing number of this H prime will be smaller than the crossing number of H mean, right? And also H prime is in F of G, right? So this gives us contradiction, right? So important issue this step is this step 2. We want to add the new red edges of vertices in VF without edge crossings, right? How can you do that? That will be the issue, right? Okay, so we need to think about two cases based on the parity of the degree of the face F. First, let's think about each case when the degree of face f is even. So we have this kind of h mean. Suppose that we have this kind of h mean, and there is edge crossing here. So we will set this face as f. Then we will remove the red edges of the vertices on the boundary of f, right? And we say this is h0. Now we'd like to add the new red edges of the vertices. First, when we add new red edges, first we want to try this face f as much as possible, right? What would be the way? That would be like this, right? So we can add 3 red edges, right? And these 3 red edges covers these 3 blue vertices, right? Okay. Then now it remains to draw the red edges of this vertex and this vertex and this vertex. So let's think about the red edge of this vertex. Can we draw? So right in this figure we can draw the red edge of this vertex here, right? So so why is it so? So that is the following. So for now the degree of this vertex in G is 5. So and by the property of two connected graph, this vertex is incident with 5 faces, right? And then since f is packed, we'd like to draw, we can only draw the red edge of this vertex outside of f, right? So the number of faces which are incident with this vertex other than f is 4, right? 5 minus 1 is 4. So there are 4 spaces to draw the red edge of this vertex. And next, let's think about how many red edges exist from how many red edges of the neighbors of this vertex exist outside of f. So for this vertex, there are 5 neighbors, right? 1, 2, 3, 4, 5. But the 3 neighbors uses the red edges inside of f, right? So only 3 neighbors has its red edges outside of f, right? So we had 4 faces outside of f, which are adjacent incident with this vertex, but only at most 3 faces are blocked by the neighbor's red edges, right? So there should be one vacant space, so we can draw the red edge of this vertex, right? So in general, this is true. If the degree of this vertex is d, then there are d faces which are adjacent with this vertex. So except for this face f, there are d minus 1 faces which are adjacent with this vertex, right? And if we count the number of red edges of the neighbors of this vertex outside of f, that should be d minus 2, because 2 neighbors draw the red edges inside of the f. So we have d minus 1 slots, but we have d minus 2 blocks. So there is one space to draw the red edge. Okay, so
when you get H0, how did you get? Did you only delete edges inside f, or you delete all the red edges associated with the vertices?
Right. So so after we picked f, now we have 6 vertices. Then we delete the 6 red edges. Okay, right. Okay. So now, we draw the red edge of this vertex. With the same argument, we can add the red edge of this vertex and the red edge of this vertex, because these are isolated. So we can draw the red edge because there is some space to draw the red edge. So let's say this is H prime. Then this is how we do the step 2 to draw the new red edges of vertices without edge crossings, right? Okay. Next case is about when the degree of face F is odd. So yeah, first we need to delete the red edges of the vertices on the boundary of F. Then the figure is like this. Then now we'd like to add the red edges of the vertices. Then first we want to use the face F as much as possible. Then the way will be something like this, right? So we can add 3 red edges here, which covers these 3 blue vertices. But there is one problem, because there are 2 vertices which are adjacent, right? So by the previous argument, so we know that for this vertex, there is one space we can draw the red edge of this vertex, right? So in this figure, that is this space, right? And for this vertex, also there is at least one face which we can draw the red edge of this vertex. In this figure, there is only this face. So the only case we can draw the red edges of this and that is like this. So we should see one edge crossing, which is not good, right? So if we have this kind of situation, then we say this is a bad case. Then we change the shape of red edges inside of F like this. From here, like this. So we rotate the red edges inside of F. Then now we can draw the red edge of this vertex here. And for this vertex, the number of faces we can draw is, so if the degree of this vertex is D, then the number of faces here we can draw a red edge is the number of faces other than F, which are incident with this vertex, is D minus 1. But since 2 neighbors uses other face, there are only D minus 2 blocks from the red edges of neighbors. So we can draw a red edge of this vertex, like the even face case. Does it make sense? Or okay, again, so even though these are adjacent, we draw the red edge of this vertex here, which is not incident with this vertex, right? So we have one space here, so we can draw the red edge of this vertex. And we need to draw the red edge of this and that. But since these are isolated, like the previous argument, there is some slot to draw the red edge of these vertices. Okay, so for any case, we can draw the new red edges of the vertices on the boundary of F without edge crossing. So which shows so until now we showed that this step 2 is true. So we can show our weak key lemma. So until now we showed a weak key lemma.
Okay. But you gotta use some point. At some point, you need to say that graph is not another cycle. So.
Graph is not a cycle.
Yeah. So maybe
not another cycle.
Right. I mean, you. Mm-hmm. So using that condition somewhere here.
Graph is not a
If
other
graph is
cycle.
uncycled, it must fail.
Uh-huh. Right, that's true. Right.
If anyway, we can figure it out.
Right, maybe, yeah, I need to figure out where that should be. Right. Okay. Then now, so our goal is to show the key lemma, and until now we showed the weak key lemma only for two connected planar graph. So now I will show a key lemma from weak key lemma. This is by induction on the number of edges. Okay, so let k is the number of edges of G. If k is 1, the only graph is k2, and k2 satisfies the statement, this statement trivially because there is no vertex of degree at least 2. So the graph itself is the edge-added graph of the original graph. So this is okay. Then now we suppose that every planar graph with at least k edges other than other cycles, it is edge-addable. So we want to show that, and we want to show that it is true for k plus 1. Let G be a planar graph with k plus 1 edges other than other cycles. First, we have weak key lemma. So weak key lemma gives that every two connected planar graph other than other cycles is edge-addable. So hence we only need to consider when G is not a two connected planar graph. Okay? So we want to show the following claim. If G is not a two connected planar graph, then G is edge-addable. Since G is not a two connected planar graph, G has a cut vertex U, right? Let's suppose that this is G, and after we delete a cut vertex, we have at least two components. In this figure, I draw components with the cut vertex. And let's take the first component with the cut vertex as G1, and let's take the remaining components with the cut vertex as a G2. So we have G1 and G2, and the number of edges of G1 and G2 are smaller than the number of edges of G, right? Okay. Then we separate two graphs by copying one cut vertex like this, and then we first suppose that G1 and G2 are not odd cycles. Then by the induction hypothesis, there exists edge-added graph H1 and H2 of G1 and G2. So from G1 and G2, we have some edge-added graph H1 and H2. So like this figure, every vertex of degree at least 2 has its red edges. Then we we merge the cut vertex like this. Then this graph is almost edge-added graph of our original graph. So what is problem? The problem is the red edge of the cut vertex. So for every vertex here of degree at least 2, it will have red edges from H1 and H2. But for the cut vertex, even though, the cut vertex may not have the red edge. Why is it so? So if this is the situation, so if the degree of the cut vertex is 2 in G1, then we will have a red edge from H1. And if the degree of the cut vertex is to the right in G2 is at least 2, then we will have a red edge here from H2. But if this is true, if this is the situation, even though the degree of cup vertex is 2, the cup vertex can't get a red edge from H1 and H2. So there is no red edge of this vertex, right? So we need to draw the red edge of this cup vertex. So we need to do that.
When you choose one of the other vertices for a cut vertex.
Sorry?
Any of those 3 vertices is a cut vertex.
Oh, so
in that case.
So this is cup vertex.
Yeah, but
the other one is also.
It's suggesting that you could just start with this other cup vertex.
Right.
Maybe it could be a vertex of degree 1 in the graph G that came anything.
Right.
Could be K2.
So yeah, that might be possible, but right. That might be make sense, but yeah. Okay, so I didn't think that way. So yeah, that might be possible. So we can first think the cup vertex like this situation. Then that might be make sense with some exceptions. Then we can think the exception separately, right? That might be possible, right? Right. Okay. Okay, so this is done. So we need to solve. So if we think this way, by fixing the cup vertex at the first step, then we need to figure out this situation, right? And what is the one more thing we need to think? That is about this assumption. So we suppose that G1 and G2 are not odd cycles. So we need to think of some other cases. So the remaining case is that one of G1 and G2 is an odd cycle, right? So this is a problem because the induction hypothesis does not guarantee the existence of an edge-added graph of GI, where simply odd cycle does not have edge-added graph. So we can't argue like before. But we will do the following. If GI is an odd cycle, we will take HI as the almost edge-added graph of GI, as below. So if there is an odd cycle, so let's start with the cup vertex. From the cup vertex, we draw the red edge outside, inside, outside, inside, and so on, right? Then this is almost edge-added, except for this cut vertex. Cut vertex does not have a red edge now, right? But other vertices will have red edges. So I say this is almost edge-added graph, except for the cut vertex. Then if we use this as HI, then we can do the following. So there is G1 and G2 here, and we consider H1, H2. But let's suppose that G2 is an odd cycle. Then in G1, in H2, even though the degree of cup vertex is 2, this cup vertex does not has a red edge. This is a kind of problem. But nice thing is other vertices of degree at least 2 will have red edges. Then we merge the cut vertex like this. Then, yeah, still there is a problem because the red edge of the cup vertex was not guaranteed. So we need to think about that. Okay, so we need to think of this case and the previous, this case, when degree is 1 and 1, right? Or when degree is 1 and odd cycle, or two sides both are odd cycles. Okay, so let's think about how to add the red edge of the cut vertex. Now the cut vertex U cannot obtain a red edge from HI if the degree of u in GI is 1, or GI is an odd cycle. But there is a good news. If either degree of u is 1 or GI is an odd cycle. Now let's think about this figure. So if the degree of u in GI is 1, we have this figure. And since there is only one neighbor of u, there is only one red edge which passes u. So the red edge of this vertex should be like this. So there is only one red edge which passes this vertex u, right?
That guy might use some other red edge as well.
Right, right. So if this, if this use red edge is inside, there is more, then there is no red edge outside, which is more better because we may have more space. But in worst case is like this. So there is one red edge in the outer face of G, right? So why this is good? Since this is true, when we consider upper side of U and lower side of U, this red edge which passes U just block one side, for example, lower side, right? So we can use this space to draw the red edge of U, right? Okay. And what about this case when GI is an odd cycle? The figure is like this. So this is cut vertex, and there is only one red edge which passes U in the outer face, right? Because the other one is in the inside of this, in the inner face. So there is only one red edge in the outer face. So we can use this upper side in this figure to draw the red edge of this vertex, right? So, and this is the only case we have. So what is the case? So for cut vertex, degree is 1 here and 1 here, or degree is 1 here and this is odd cycle, or two things are odd cycle. For any case, after we contracting the cut vertex, the red edges which passes this cut vertex just hide one side, right? So we can draw the red edge of this cut vertex in the upper side, like this and that. So we can draw the red edges. Hence, what we showed was the following. For cut vertex, if there is a red edge of the cut vertex from H1, H2, then which is good, that is good. But if there is no red edge of cut vertex, we can draw the cut vertex, the red edge of the cut vertex. So therefore, every planar graph G, other than odd cycles with size of G is k plus 1, has its edge-added graph H. Right. So therefore, we showed the following. So we showed the key lemma stating that every planar graph other than odd cycles is edge-addable. Right. So this is the finish of the proof. So right. So maybe, so I made this slide, but maybe you want to ask what will be next problem about this direction. So one problem will be graphs, the family of graphs of a given surface. So in this talk, we consider the planar graphs, right? But we can think different surface, right? And we can pick some surface as a different one, and we want to find the upper bound of dynamic chromatic number. For chromatic number, that was done by, that was done in some sense, so we can try to do that. And one more problem might be adding some extra condition. We want to reduce the upper bound of dynamic chromatic number. Like, for example, we can add some girth condition. So, and then we want to try to reduce the upper bound of dynamic chromatic number for planar graphs. That kind of thing could be next problem. Thank you.